Welcome to our lecture video in fluid mechanics, and in this video we will solve the 3 sample problems in our handout under the topic buoyancy. Okay. So Archimedes' principle states that any body immersed in a fluid is acted upon by an upward force, or that is the buoyant force, equal to the weight of the displaced fluid. And here in this figure, you can see a submerged body wherein the weight here, the weight W represents the total weight of the material, whereas the buoyant force here represents the volume of the displaced fluid here. So it's equal to, so this is the formula, weight is equal to buoyant force, wherein weight is gamma times the volume, wherein gamma is the unit weight of the body being submerged and V is the total volume of the body. So gamma of the body then volume is equal to, how about this one? It is the gamma of the fluid displaced. Okay? Gamma of the fluid displaced multiplied with the volume displaced, or the volume of the body that is immersed. So here in this example, in our figure, the volume here that is submerged in the liquid. So let's answer the 3 sample problems. The first one, a hollow cylinder 1.2 meter diameter and 2 meters long weighs 3.5 kilonewton. How many kilonewton of lead weighing 110 kilonewton per cubic meter must be fastened to make the cylinder float vertically with 1.5 meters submerged in fresh water when the lead is, letter A, fastened to the outside bottom, so outside of the hollow cylinder. Letter B, it is placed inside the cylinder. And letter C, from the setting at B, or from the answer at B, what additional load must be placed inside the cylinder to make the top of the cylinder flush with the water surface? Okay, so here is our hollow cylinder with the diameter of 1.2 meter. So here is the diameter of 1.2 meter. Okay. So it says there for the letter A, so it's asking how many kilonewtons of lead, given the weight for the lead of 110 kilonewton per cubic meter, so that this cylinder will float vertically with 1.5 meter submerged in fresh water. So we will answer this based on our formula for buoyancy. But so where is the lead located? It is fastened outside the bottom. So the lead is fastened outside the bottom. So let's say this is the lead. So with unknown shape and volume. So this is our lead. There. Therefore, the forces that we can see here. So what's the height of this cylinder? Height of the cylinder is 2 meters. Or it is 2 meters long. So here are the forces present. The weight, of course. The weight of the cylinder, say that is weight 1. Then we have the weight of the lead, say that is weight 2. Then we also have here buoyant force 1. So the buoyant force 1 for the lead, for the cylinder, and for the lead we have buoyant force 2. Okay, so let's equate it. But first, let's find the values for W1. So this is W1 from the given here in the problem. So the cylinder, hollow cylinder, is weighing 3.5 kilonewton. Then for the weight of the lead, it says there it is 110 kilonewton per cubic meter. So you need to find the volume. Therefore, your W2 is equal to 110 volume. 110, let's just say volume there. And then we have buoyant force 1. Buoyant force 1 is the volume submerged. So the volume of the body submerged multiplied with the gamma of the liquid where you have submerged that portion of the body. So since we are talking about fresh water, our gamma here, so this is gamma volume. So buoyant force is 9.81, and the volume of the submerged cylinder, that is pi over 4, the diameter 1.2 meter squared, and then the height of 1.5 meter. So buoyant force 1 now is equal to 16.64 kilonewton. Next, we get the buoyant force 2, the lead. Buoyant force for the lead is gamma volume also, and we don't know the volume for the lead, therefore we just say 9.81 to where it is submerged, and then the volume of the lead. Okay, so that's all the forces involved. So this time we have the summation of forces vertical is equal to 0, say downward positive. So every downward force is positive. We have W1 plus W2 minus buoyant force 1 minus buoyant force 2. That is equal to 0. W1 is 3.5 kilonewton plus W2 is 110, the volume of the lead, minus the buoyant force 1 is 16.64 minus 9.81 volume for the buoyant force 2. Therefore, we can now get the value for volume. So volume now is equal to 0.1312 cubic meter. Therefore, the weight now, so it's asking the weight of the lead. So that is the W2. Weight now of the lead is equal to the W2, okay, is equal to 110 times the volume, 0.1312, and that is equal to 14.432 kilonewton. So that's for letter A. Now for letter B, the condition here is, so what should be the weight of the lead in order to have it floating vertically with 1.5 meters submerged, and the lead is inside the container. So inside the container. So for letter B, so here we have the cylinder again. So this is the height of the cylinder, 2 meters. And the lead is inside. So the lead with unknown volume and shape. So this is now the lead. So the forces present in this figure is the weight of the cylinder. So that is W1. The weight of the lead, W2, and the buoyant force only one buoyant force, that is buoyant force of the cylinder. Why only one buoyant force? Because the lead is inside the cylinder. The lead is not exposed to the liquid or the water. Therefore, the only body exposed to the water here is the cylinder. So only one buoyant force. So summation of forces vertical is equal to 0, let's say downward positive. So W1 plus W2 minus the buoyant force equals 0. So W1 a while ago, that is 3.5 plus, now W2 is missing because that is the weight of the lead, minus the volume submerged multiplied with the gamma of the liquid, which is water. So 9.81 times the volume submerged. So pi over 4, then the diameter is 1.2 meter squared, and it is submerged in 1.5 meter high. It's equal to 0. Therefore, we now have the value for W2 as 13.14 kilonewton. So that's for letter B. Now for letter C, what's the condition for letter C? From the answer at B, what additional load must be placed inside the cylinder to make the top of the cylinder flush with the water surface? So how does we look at it? So here it's already flushed, okay? Meaning the surface or the top of the cylinder has reached the surface of the water. So this is 2 meters submerged. Oh, already there. 2 meters is submerged, having the lead inside from the situation at B. So this is the lead. So is there what additional load? So there's no known volume, no known shape. So whatever volume is that. So what additional load? So what forces are present in this figure? So we have again the weight of the cylinder. So W1, the weight of the lead. So weight of the lead as W2, and the additional weight as W3. So W3 is the additional weight. And the buoyant force here is only 1. Why only 1? Again, all these materials, the lead and the additional force, additional load is inside the cylinder. Therefore, the only body that is exposed in the water is the cylinder. Therefore, only one buoyant force can be seen here. So again, summation of forces vertical is equal to 0, downward positive, W1 plus W2 plus W3 minus buoyant force equals to 0. This is 3.5 plus W2 says there from the answer at B. So that is 13.14 plus the unknown W3 minus the buoyant force of this, of course, that is gamma volume, gamma of the water, and then the total volume of the submerged cylinder, pi over 4, diameter 1.2 squared times 2 equals to 0. So what is W3 now? The additional load, that is 5.55 kilonewton. So that's example number 1. Now let's go to example number 2. Two spheres, each 1.3 meter in diameter, are connected by a short rope. One weighs 12 kilonewton and the other weighs 5 kilonewton. When placed in water, compute the first, tension in the rope. B, depth of flotation of the 5 kilonewton sphere. C, volume of sphere exposed above the water. Okay, so we have two spheres, each they have the same diameter of 1.3 meter. They are connected by a rope, a short rope. Now one of the cylinder weighs 12 kilonewton and the other weighs 5 kilonewton. So which of these two cylinders weighs 12 kilonewton and which weighs 5 kilonewton? We can check that by computing for the gamma. So let's compute for the gamma here. If the gamma of these materials, okay, so take note, if the gamma of these materials is lesser than the water, therefore it is less dense, right? Because the denser the material, the more it submerged to the liquid or the water. Okay. So let's compute for the volume. Okay. So what is the volume sphere? Let's compute first for the volume of sphere, that is 4/3 pi r cube. So that is 4/3 pi of r, so that is 0.65 cube. So what's the volume of the sphere? So this is 1.3 meter diameter. So the volume of the sphere is 1.15 cubic meter. Now let's compare gamma 1. So let's have the gamma 1, which is the one weighing 5 kilonewton over, so that is weight 1. Say weight 1 over the volume 1. So the weight 1 here is 5 kilonewton all over 1.15 cubic meters. What is the answer here? That is 4.35 kilonewton per cubic meter. And this is less than the gamma for water. Therefore, it is partially submerged. Let's compare for the gamma 2, that is weight 2, volume 2, or same volume. Actually, they have the same volume, so let's not differentiate it. So that is 12 kilonewton, 1.15 cubic meter. That is equal to 10.43 kilonewton per cubic meter. And this is greater than gamma of water. Gamma of water being 9.81, right? So 9.81. Since it is greater than the gamma of water, therefore it is totally submerged. Yeah. So this is the reason why the figure looks like this. One of the spheres is partially submerged and one is totally submerged. Therefore, we have here weight 1 as 5 kilonewton and then weight 2 here as 12 kilonewton, which is totally submerged. Therefore, since two bodies here is exposed in the water, therefore we have buoyant force here. So buoyant force 1 for the sphere 1, and then buoyant force 2 for the sphere number 2. So this is sphere 1, this is sphere 2. Okay. And it's asking for the tension in the rope. So the tension in the rope here is that when we cut here, so if we cut it here, so what will happen? So if there is a cutting here, the tension will go in this direction. Okay. So let's cut it. So letter A. So for us to compute for the so this is the sphere number 2. This is sphere number 2. When we cut it here, when we cut the rope here, what will happen in this sphere? Okay. So we have the weight. So this is the tension here. The tension is upward. Okay. Then weight is downward. Weight 2, which is 12 kilonewton. Then the buoyant force 2. So summation of forces vertical is equal to 0, upward positive. So that tension is positive plus buoyant force 2 minus weight 2 is equal to 0. Tension plus buoyant force is gamma of water times the volume minus W2 is 12. So tension plus gamma of water is 9.81. The volume of the sphere totally submerged is 1.15 minus 12 equals 0. So what is tension? So that is equal to 0.72 kilonewton. So that's for letter A. What's question B? Depth of flotation of the 5 kilonewton sphere. So it's talking about this, the 5 kilonewton sphere. So depth of flotation. Oops. Or B. That's the sphere number 1. So the weight here, of course, weight of the sphere, W1 is equal to 5 kilonewton. And the tension, of course, the presence of the tension, we have cord here, right? But here, the tension is going downward. Okay. Then buoyant force is upward. Why is the tension going downward here? Because the tension tends to pull, okay? Tends to pull the rope. So the rope, when you pull it, it goes downward. Whereas here in our cylinder or in our sphere number 2, when you pull the rope is moving upward. Okay? So that's why we have those directions. And of course, the value that we got here is the same value as what we will put here. Okay? So they are the same. They are of equal value. Okay? And this letter B is asking for the height h here. the depth of flotation h. So how do we solve this? So how do we get this one here, this portion here? This is not half of a sphere, but rather we have here a spherical segment. So what is the volume for spherical segment? So volume S is equal to the volume of spherical segment of one base. This have only one base, this spherical segment. So Vs is equal to pi h squared over 3 times the radius of the sphere minus the h. Okay. Summation of forces horizontal is equal to 0, vertical. Summation of forces vertical is equal to 0, having downward as positive. So we have W1 positive plus tension positive minus BF or buoyant force is equal to 0. So W1 is 5 and value for tension is 0.72. So 5 plus 0.72 minus the buoyant force here is the gamma times the volume submerged. Gamma of the liquid 9.81. Then the volume submerged is the volume of the spherical segment. So pi h squared all over 3 times 3 times the radius. The radius a while ago is 1.3, right? So 1.3 divided by 2 minus h. There. So this is equal to 5.72 minus 9.81 times, this is pi over 3 times 3 times 1.3 divided by 2. This is 2.042 h squared minus pi h times h. So that is pi 3h cube equals 0. And then we have here 5.72 minus, distribute 9.81. So that is 20.032 h squared plus 10.273 h cube equals 0. So this is now 10.273. So you can use shift solve here if you have shift solve in your calculator. This is but if none, you can use the equation 0h plus 5.70 equals 0. Mode degree 3. Okay, it is 10.273 equals negative 20.032 equals 0 equals 5.72. So 1.773 for H1, 1.773 meter. For H2 is equal to 0.656 meter, and for H3 that is negative 0.479 meter. Okay. Obviously, we're not going to use the negative sign here, and H1 is greater than the diameter, which is 1.3 meter diameter. Therefore, this is not good. Therefore, the one left here is this. This is the answer. That's for letter B. Let's go to letter C. Volume of sphere exposed above the water. The volume of sphere exposed above the water. This one here. So, BE. So, in order to get the value for BE, let's find here HE. The height exposed. So, you can have additional space. For letter C. So for letter C, H exposed is equal to 1.3 minus H. And that is equal to 1.3 minus 0.656. H exposed is equal to 0.644 meter. Therefore, continue here. Volume of the exposed now here is the volume of this spherical segment with base 1. So pi h1 squared over 3, then 3r minus h1 or he, say he. So we have here pi 0.644 squared all over 3 times 3 times 1.3 divided by 2 minus HE 6.644. So what's the answer here? Volume exposed is now equal to 0.567 cubic meter. So that's for example number 2. Now let's go to the last example for this video. From the figure shown, the gate is 1.5 meter wide. So the gate is 1.5 meter wide. This gate, it's talking about this gate. This gate here. That is 1.5 meter wide and is hinged at the bottom of the gate. So hinge here. So hinge. Compute the hydrostatic force acting on the gate. So, since the water surface is only here, therefore, the area that we are going to solve is here, the projected area. Right? So, this is the projected area. And the width here is 1.5 meter wide. So that is 1.5 meter wide. So that is when you're looking at this. Okay. Hydrostatic force acting on the gate for letter A. Its line for B, its line of action from the water surface. And letter C, minimum volume of concrete, this concrete here, needed to keep the gate closed given the gamma of concrete. Okay. So we have a pulley here. So observe the mechanism. This is the gate. We have a pulley and this is the rope. And here is the concrete. So force F. So this is our force F, hydrostatic force. So letter A, F is equal to gamma of water HCA. So the center of gravity is here, center of pressure. Therefore, our HC is here, HC. This is 2 meters. So gamma of water is 9.81. HC is 2 divided by 2. The area is 1.5 by 2 meters. So F now is equal to 29.43 kilonewton. Now letter B, the line of action from the water surface. It's talking about the hydrostatic force. What is its line of action from the water surface? It's asking for the Y here, the Y here. It's asking for Y. Now if from the bottom, this is 1/3 of H, so what is Y? So from the bottom, it's 1/3 of H. How about Y? Y is then equal to 2/3 of H. Remember that the reason here is that the pressure is uniformly varying. So it is just right to say that the Y here is this 2/3 of the total height, because the center of gravity for the triangle, okay, is 2/3 from the apex, from this point. Okay, so our line of action Y, so Y is equal to 2/3 of H. So 2/3 of the H here is 2 meters, so that is 4/3, or that is 1.33 meter. Okay, so letter C, what is the minimum volume of concrete needed to keep the gate closed? So what are the involved here? What are the involved forces? So if you look at this portion here, so if you look at the entire mechanism, you can observe that there is the presence of tension force here. So the presence of tension force. Tension. And the presence of force F here. So how do we get the value now for the tension? If we're going to make a summation here at the hinge, okay, by getting this portion here. If we concentrate here by cutting the rope here, so we can have the tension here. So tension T. Then you have the weight of the concrete. So the weight of the concrete, W, and you have the buoyant force, BF, here, upward force. Let's cut that part. So letter C, so it looks like this. So this is the concrete. We have the weight of the concrete, W. We have the buoyant force, upward. Then we have the tension from the rope. Therefore, doing a summation of forces, vertical is equal to 0, upward being positive, we have tension plus buoyant force minus W equals 0. So the tension here is missing. So how do we get the value of tension? So from summation of forces here. Summation of force. So, what's the summation of forces? Let's redraw it here. Tension. Then we have the force F here. Force F, tension T, the distance, when we're talking about the distance, this is 1/3. So this is 1/3 of, or h over 3. So h over 3 is equal to 2 over 3. And then here, what's the distance for this? So what's the distance for this is 0.5 plus 2. So that is 2.5. So it is 2.5 meters. Therefore, summation of moment at O here, this is O, the hinge, is equal to 0, being positive counterclockwise, so that tension is positive. Distance from the hinge, 2.5 meters, minus F times 2/3 of h. No, 2/3, just 2/3. So 2/3 equals 0. So tension, 2.5 minus the force that we got a while ago, that is 29.43. 29.43 times 2/3 equals 0. Therefore, tension is equal to 7.85 kilonewton. So, using the value of tension, you can use it here now. 7.85 kilonewton plus buoyant force here is equal to the liquid, the gamma of liquid, times the volume submerged, the volume of the concrete, which is being asked in the problem, right? The minimum volume of concrete. So volume equals gamma of concrete, then volume of concrete. So 7.85 plus 9.81 volume of concrete equals gamma of concrete is 24, then volume. Therefore, we now have volume equal to 0.55 cubic meter. Okay, so that's for example number 3. Okay, so that's all for